One of the most important challenges to image stabilization for large, deployable space-based optical systems is the control and mitigation of vibration across the frequency spectrum, and especially in the front-end optics. The purpose of this demonstration is to evaluate the precise benefits of vibration control in two key areas: active damping of the secondary mirror support structure and isolation of the front-end optics from the spacecraft. The test setup consists of a subscale quadrupod secondary mirror support mounted on a bench that can be vibrated to simulate the motion of the spacecraft during operation on orbit. For the purposes of this experiment, the structure is a dynamic replica of a typical full-size telescope. The experiment uses a helium-neon laser which forms two beam paths, a reference beam path and a test beam path. The reference beam path measures the motion of the base on which the telescope is resting, and the test beam path measures the telescope pointing. The purpose of the experiment is to demonstrate technologies that have been developed for both active damping and isolation of telescope structures in the presence of spacecraft-induced disturbances. To provide active damping, Piezo ceramic actuators and sensors have been bonded to the quadrupod secondary mirror support structure. When vibrated, the piezo ceramic sensors generate a voltage. It is amplified, phase shifted, and then fed back to the actuators, which generate a force that cancels the motion of the support structure. The result is active damping at the vibrational frequencies of the quadrupod. This technology is space-proven. Active members with piezo-ceramic sensors and actuators embedded in the composite have been operating on orbit for more than 3 years, under extreme temperatures of plus or minus 100 degrees centigrade. In order to isolate it from the spacecraft, the telescope is attached using a hexapod, a sequence of 6 struts that together form a kinematic mount between the spacecraft and the front-end optics. There are 2 levels of isolation. Passive isolation is achieved with a very soft spring, along with viscoelastic damper elements which shear and absorb energy. These passive isolators are space-qualified. 36 of these devices are flying on the Chandra X-ray telescope, launched in 1999. They are arranged in hexapods to support the 6 reaction wheels which precisely orient the Chandra Observatory. In addition to passive isolation, systems having high vibration levels would utilize active force feedback isolation to cancel the vibrations as they occur and stabilize the telescope. This active isolation employs a move-out-of-the-way controller. The principle of the move-out-of-the-way controller is to shorten or lengthen the strut in a way that cancels out the base motion and maintains the telescope in a stabilized condition. To implement this control, there is a force sensor on each of the 6 struts. Within each sensor is a piezo-ceramic material which reacts to axial force in the strut by generating a corresponding level of voltage. This voltage is the input signal to a voice coil actuator which counters the forces in the strut. In the next phase of the experiment, the telescope is hard-mounted to the optical bench using 3 A-frames which will transmit forces in a very rigid manner to the front-end optics. The bench is then shaken at a frequency that coincides with the resonance of the secondary mirror support structure. The beam on the right shows the base motion, and the beam on the left shows how resonance in the telescope structure can amplify the line-of-sight pointing error. Now, by turning on active damping, telescope motion can be reduced significantly, so now it's just about equal to the base motion with very little amplification. Active damping has been shown to be particularly effective in mitigating resonant vibrations in large structures. In the next portion of the demonstration, the bench is shaken by a random vibration input. This source is scaled up considerably for the purposes of visualization. Once again, the beam on the right shows the base motions. The beam on the left is the telescope output, with higher frequency motion significantly amplified by the telescope dynamics. The first layer of control is active damping on the piezo patches. When this active damping is turned on, much of the high-frequency motion on the telescope output is eliminated. An analyzer trace shows the base input, or laser reference beam. Vibration amplitude is in the vertical axis. Vibration frequency is the horizontal scale, with the higher frequencies on the right. This trace is a measure of the telescope pointing, with its support structure hard-mounted on the bench, and no active damping. When the telescope pointing motion is overlaid on top of the base input, it can be seen that the 12 Hz mode is being amplified by several orders of magnitude by the telescope dynamics. With active damping activated, the peak power spectral density is reduced by 3 orders of magnitude. For the next phase, to demonstrate the effects of isolation, the hard mounts are removed so that the telescope structure is supported on the active-passive isolators. In addition to active force feedback, a loop is closed between the optical image and the actuators, further contributing to inertial stabilization. The analyzer trace shows motion reduced even further. And at 12 Hz, there is a 6 order of magnitude attenuation in power spectral density, or a factor of 1,000 in amplitude. The combination of active-passive isolation and active damping has made a factor of 1,000 reduction in motion, and this corresponds to a reduction in pointing error from 7 arc seconds to 12 milli-arc seconds. High-frequency vibrations have been virtually eliminated, which means that the pointing control system will not have to compensate for resonance in the secondary mirror structure. Low to mid-frequency vibrations have been attenuated by an order of magnitude, and this brings telescope pointing error easily within range of the fast-steering mirror, which can maintain the image precisely on the focal plane. Multi-layer vibration control can significantly improve spacecraft telescope performance. Vibrations are mitigated at the source and then sequentially reduced as they attempt to propagate through the optical support structure. The multi-layer strategy works in conjunction with the other spacecraft pointing systems to provide agility with extreme pointing precision.